All right, welcome to the Explainer. Today, we are diving headfirst into Swift's modern concurrency system. And let me tell you, this isn't just a minor update, it's a total game changer for how we write code that does multiple things at once, really designed for safety and performance right from the very beginning.
So let me ask you this. Have you ever been completely sunk by a data race? You know that feeling, right? Those mysterious crashes, the tests that only seem to fail late on a Friday, when your data just seems to corrupt itself for no good reason. It's one of the absolute hardest things to track down in your code.
Okay, so to really get our heads around this, we're going to borrow a great analogy, one that Apple's own engineers use. Welcome to the Sea of Concurrency. Think of it like this. It's a place with incredible power. You can get so much done at the same time, but it is also packed with hidden dangers.
And the absolute biggest monster lurking in these waters? It's the data race. So what is that? It's when you've got multiple threads, all trying to mess with the same piece of memory at the exact same time, without any kind of coordination. And at least one of them is trying to write to it. The result? Pure chaos. Your app state gets completely scrambled, and that leads to some of the most unpredictable crashes you'll ever see.
So, how did we used to handle this? Well, for a long time, we navigated these treacherous waters with tools like Grand Central Dispatch, or GCD. And look, GCD was incredibly powerful, but it had these hidden performance pitfalls. You'd give it some work to do on what's called a concurrent queue, and more often than not, it would just spin up a brand new thread to handle it.
And that led to a massive problem called thread explosion. Just imagine this. One of your threads gets stuck, right? Maybe it's waiting for a network call to come back or for the database to find something. What did GCD do? Well, its solution was often just, hey, let's create a new thread to keep things moving. And if that one got stuck, you guessed it, it would just make another one and another.
So what you ended up with was a massive traffic jam at sea, just a whole ocean full of these blocked threads. That's the thread explosion you see there on the left for the old GCD way. And every single one of those threads takes up memory. And the system has to pay this huge cost just constantly switching between all of them. But now look at the right side. The new Swift tasks model, it uses this really smart cooperative system to completely avoid this mess. And that's what we're going to dig into right now.
So yeah, to solve this huge maritime mess, Swift 5.5 came along and introduced a totally new model, complete with a new kind of boat to do our work. And this is what we call structured concurrency.
And these new boats? They're called tasks. So just think of a task as this little self-contained unit of work that can run asynchronously. It has a job to do, and it just does it from start to finish, all on its own.
And this right here, this is the magic of the whole new system. It all hinges on this one key word, await. See, await is what we call a potential suspension point. When a task gets to an await, it doesn't just stop and block the whole shipping lane like the old threads did. No, it politely pauses, it yields the thread to another task, and it lets other work happen. And then, once its data is ready, it just picks up right where it left off. No more blocking, no more thread explosion. It's kind of genius.
And there's a reason they call it structured concurrency. It's because these tasks all live inside a hierarchy. So a parent task that kicks off a bunch of smaller child tasks, it knows about all of them. And that's huge, because if you cancel the parent, guess what? All its children are automatically canceled too. And if one of the kids runs into an error, that error bubbles right up to the parent. It makes managing really complex work so much more predictable and, frankly, safer.
Okay, so we have these great new boats. They're fast, they're efficient, but what good are a bunch of independent boats if they can't even talk to each other or, share their cargo? Figuring out how to safely pass data between these tasks is the next big piece of the puzzle.
All right, let's talk about cargo. First up, imagine sharing a pineapple. Now in Swift, a pineapple is kind of like a struct. It's a value type. So when one boat gives a pineapple to another, it's not giving it the same pineapple, it's handing over a perfect copy. Now each boat has its own unique pineapple. If one captain decides to slice theirs up, it has zero effect on the other boat's pineapple. It is inherently safe, no confusion.
But sharing a chicken is a whole different story. A chicken is like a class in Swift. It's a reference type. And when you pass a chicken from one boat to another, you are not passing a copy. You're passing a reference, basically a map that points to the exact same chicken. So now you have two different boats trying to interact with the same animal, maybe at the same time. This is what we call shared mutable state, and it's the perfect recipe for a data race.
And this is exactly where the sendable protocol comes to the rescue.
Think of it like a special stamp or a label that you put on your cargo. It's a promise you make to the compiler saying, hey, this type, like our pineapple, is safe to be copied and shared between tasks without causing a data race. And you might have guessed, our chickens, by default, they are not sendable.
Now here's the best part. The Swift compiler itself turns into this super helpful but very strict customs inspector. It literally checks every single piece of cargo you try to pass between your tasks. And if you try to sneak something non-sendable, like our chicken, from one task to another, nope, the compiler will stop you dead in your tracks with an error before you can even run your code. It's amazing.
Okay, but let's be real. Sometimes you do need a shared resource. What if you have a whole flock of chickens that tons of different boats all need to interact with? But they have to do it one by one, in a safe and orderly way.
Well, for that, Swift gives us another new tool, actors. And in our C analogy, actors are like these special, protected islands of isolation. They are these self-contained places that protect their own state, so in this case, their flock of chickens, from all the chaos of the open sea. So here's how an actor works. A boat, our task, needs to do something with the chickens, so it sails up to the island. But to get on the island and interact with its state, it has to await its turn to dock. The actor enforces one simple, unbreakable rule: only one boat at a time. Every other boat has to wait in a nice, orderly line. This system of synchronized sequential access completely 100% eliminates data races on the actor's state. So, let's pull it all together. What we have now is a complete, modern toolkit for navigating this sea of concurrency. We've got our tasks. Those are efficient, non-blocking boats. We've got Sendable, that's our safety protocol for all our cargo. And we have Actors, a protected islands of isolation for managing any shared state. It's a full system.
And you know, this isn't just some academic theory. This is the new standard across all of Apple's platforms. The core frameworks you're using every single day, I'm talking URL session for networking, core data for your database stuff, they've all been rebuilt from the ground up to use this modern async await approach.
Just like Apple said when they introduced this, it fundamentally changes how we build our apps. We're not just hoping we get it right anymore. This system gives us data race safety by design, and it's enforced by the compiler itself, not just by some convention or trying to remember to use manual locks, which is so easy to get wrong.
So look, by really understanding these core ideas, tasks, Sendable, and actors, you can now write code that isn't just faster and more responsive, it's also dramatically safer and just easier to think about. The C is still big and powerful, for sure, but now you have a modern fleet, you have reliable maps, and you can navigate it with total confidence. So the only real question left is, what are you going to build?